Right, that's okay. All right, good. What else do I need to do? Go back to this. Let's see, yeah, hide that. And then put a few of these. So let me just look before I start the stuff. Well, let me download the thing first. All right, so I wanted to do dynamics. I'm going to hide this. Then there's a lot of these. The Polymer dynamics thing is kind of indecipherable. And there's two of these rouse things. Oops, I didn't want PDF. I wanted this thing. And then there's a new rouse. Then this heat capacity thing. You see there's machine learning and nanocomposites in here. Then this thing, the CR chapter 8A is Rubinstein and what's the C part? Anyway, it's that book. So it's basically goes through dynamics. So if you can't understand what I say, there's this book. It's pretty easy, I guess. So I guess I'm not exactly following that, but I think that might be helpful. And then I'm going to open these guys. So that's, are they all open or? Oh, here they're open. All right, then the homework. Let's see. So does he? Let's see. The homework 8. This thing. So does he say the cross-link density? No. This says cross-link. And there's only one place where it says cross-link. We'll take density. Nope. And then right, so you know the molecular weight between cross-links, right? Same total molecular weight. So a 4 arm is 20K. So that means 1 arm is 5, and then 2 arms connected would be 10K. And then you could go, it's a good solvent. So you know molecular weight, and this is polyethylene oxide, right? So you need to know the Kuhn link. Polyethylene oxide is 7.6. The Kuhn link is 7.6, if you can believe that. So you have, let me see for a second there. Let me see, just hold on a second. Oh, 7.6 angstrom is LSA. And then, oh, then it should be shown. See, what's really auto. Oh, all right, those purposes there. And then it's 10K between the cross-links, right? And then the PEO is carbon-carbon oxygen, so it's 10 grams per mole. And then that's like 24, 28 for the hydrogens, and then 16. Right? And it's 44 grams per mole. So, and you have 10,000. So 10,000 divided by 44 equals something. So let me just ballpark what it should be. Okay, calculator. Nope, wrong thing. That gives me 230 Kuhn units. That's N, right? So if I say the distance between the two is n to the so r equals n to the 3/5 times 7.6 angstrom, and it's 230. Yeah. And then it's 26 times 7.6. So it's about 200 angstroms. And then that cubed is 8 times 10 to the 6 cubic angstroms. And then we want that in let's see, so that's the volume. What the volume? That's the volume per crosslink. It's grams per mole, moles per volume. So we have what, moles per volume, right? And I have all the volume. So I had, and that's for 1 mole. So then just 1 over that gives me the crosslink density the way he's talked about it. So it's 8 times 10 to the minus 6. So let me convert this to centimeter cubed. So it's 10 to the 8, I think. 10 to the 8. It's 10 to, no, wait, no. It's 10 to the 4 to microns. And then microns to centimeters is 5, right? So it's 10 to the 9. 10 to the 9, and I have 8 times 10 to the 6. So it's 8 times 10 to the minus 3 centimeter cube. And if I flip that over, it's flip that over, it's 125 moles per centimeter cubed. Doesn't seem to agree. And we got 0.4. I think we got 0.4 mole per centimeter cubed. Somehow I did the math wrong. Anyway, maybe you could do it right. I got 0.4. I get in the chart we got 0.4. This is 125. So a significant problem here. It isn't even like 400. So it'd be like some 10 to the 9 thing is wrong or something. So anyway, that's the best I can do offhand. But that's the idea. Like you just would do something like that. You could calculate from his thing what the crosslink density should be, and then that could work out, but apparently it didn't. So anyway, so there's that business. Any other things on that homework? I don't know. Hopefully the rest is okay. No, email me if it isn't, right? So all right, so we got this dynamics thing. I think this is, I want slide 38 on this. I was going to include this in the other thing, but yeah, the Dubai thing. And then these other guys. So I got this thing, Rouse model, and then there's another Rouse model here. All right, so the Zim model, you just take the coil and you say the solvent or whatever is within it. So the coil is just the coil size, right? And then you say, so the R, you can get the diffusion coefficient by KTO with friction factor. This is the coil size, which is B into the 1/2 if it's Gaussian, right? Or if it's, so basically the diffusion coefficient is going to go with n to the -1 by df. And then the relaxation time is n times that friction factor. So that's going to give you n to the 3 by df if you do that. So this is 1 by df, and then n is let's see, how does this work out? This is our 3/2. Let's see. R, it's just R, right? R should be n to the 1/2. Oh, n times R is n to the 3/2, because it's 2/2 plus 1/2 gives you 3/2. So it gives you the relaxation time to go into the 3 by df. And then the viscosity, so the viscosity is going to be basically the coil is going to just be proportional to the 1 over the overlap concentrations. You get something like that. So that's a Zim model. It could have a coil that doesn't, and the other model is it totally drains. So this is non-draining, and the other one is totally draining, which would be just, it's a train and it's got cars. So in that case, viscosity just goes with the molecular weight to the power 1. And then this tau ends up going to into the 2. So you end up with this business. So this is a measurement of tau for a polymer melt, and then this is a power 2 for tau. So that differs from the Zim thing. It isn't 3 by df. That was 3/2, 1.5, it's 2. And the 2 is predicted by basically the Rouse model predicts into the 2 for the relaxation time. And then it gets the relaxation time, and then it predicts the diffusion coefficient. So that's significantly different than diffusion coefficient here. And then it predicts that the viscosity is going to go to the power 1, not to the power 0.5 or 0.8. Oops. All right, so the 2 models end up giving quite a bit different dynamic properties, like viscosity, relaxation time, and then this diffusion coefficient. Right, so that's kind of the gist of this. So also the other thing is that like this doesn't work. Like it only works up to a certain molecular weight. So if this is polyethylene, this is wax. It's like candle wax, right? And this gets up to a molecular weight of 100 or 10,000 grams per mole, which ends up like 100 units. And then all of a sudden you get entanglements and this thing takes off, and it's on a log-log plot, so it significantly takes off over the power 1 that it would have been because of the entanglements, right? So this part was kind of solved more or less using reptation. And this part was solved in kind of 1953 by a guy named Rouse, right? So Rouse was at Illinois, and then he went to Philadelphia and worked at the Franklin Institute, which is now a museum. But at the time it wasn't. And then the research part of the Franklin Museum, University of Delaware bought it or something. So it went to Delaware. So anyway, Rouse's place doesn't exactly exist anymore. There's a museum there. But anyway, so this was 53, okay? So, and the Rouse model is kind of this thing. So you say the chain is made up of beads, and then so you have bead where you are, ZL, there's a bead before, the bead after. So the beads are hooked together by springs. There's a spring constant, and then the distance between the beads. So be ZL plus 1 minus ZL times the spring constant gives the force. And then for the other bead, it's ZL plus 1, ZL minus 1 minus Z gives you the times spring constant gives you the force. So the bead's trapped between 2 springs, and it could oscillate like that. It's bouncing between the beads. You can do that for all the beads of a chain, right? So, and that force, that spring force has to equal the friction factor times the velocity. That's the Rouse model. Okay, so this thing, all right, so this is 1953, he publishes this thing, but back in the old days, so 1912 in Zurich, at Zurich University of Zurich. So Zurich has 2 schools. It's got ETH, which is like the MIT of Europe, kind of. There's 2 ETHs, one's in Zurich, one's in Lausanne. Switzerland has 4 languages: German, Zurich, and Bern, capital, and then Geneva, French, right? Geneva, Switzerland, and Lausanne is a small city in Montreux, like along Lake Geneva, and Mount Blanc is there. Then they also speak Italian. So there's 2 cities in the Italian part, and they speak Romanesque, which is like their own language. Some weird language is a mountain language. But you get up into the mountains and people are a little isolated. So they have their own language. So there's 4 languages there. Anyway, so the German part is where like Debye and Volta was there. Like a lot of Nobel laureates were there. But this is 1912, long before Debye won the Nobel Prize in like, well, he died in 66. I think he won Nobel Prize in 40 something, late 40s. Once he was in the US, he won the Nobel Prize. And so anyway, so he was at University of Zurich. Then he went back to the Netherlands, where he was from. And then like in third, so there was a world war in between there, right? Right around that time was World War One. And then he went back to the Netherlands after World War One, like where he was from. And then 38 or something, he goes back to Zurich, like, because basically things are getting hot again in that part. And Switzerland is a neutral country, so you can go there and live happily, even while everyone's like in trenches killing each other, or whatever they did in World War II. But during World War II, he went back to Germany. So he kind of got sucked into the Nazi thing. Then he ended up in Berlin, and then things got too hot for him. And then he came to Cornell, like right when Hitler was taking power. Things got really dicey for everybody. And then he came to the US. There was a lot of fleeing of scientists, you know. So supposedly he took all the money he had and he bought gold and he made coat hangers out of it. And he took his clothes on coat hangers and all his money was in the coat hangers. Made gold coat hangers. I don't know if that's true, you know, because gold wouldn't make a good coat hanger because it's too malleable, you know. But anyway, that's the story that he brought everything to the US. He went to Cornell, right? Which is where he published this thing. So all right, so first off, heat capacity seems to have nothing to do with polymer dynamics, but the model's almost exactly the same. So you have, this is Debye's model for the heat capacity. So he's got beads and springs, and he has a spring constant, and he has the same equation. It's exactly the same equation, except on this side, instead of saying velocity times the friction factor, he says mass times acceleration. So the same like force balance, but he's got mass times acceleration because what he wants to get out of this thing is like the relaxation time of the thing in terms of the mass. Because for heat capacity, it's atomic. So these are atoms, and these are the forces between atoms. For polymer, so his model was a linear polymer, linear chain originally, you know, for heat capacity. And then he expands that to 3D and he gets his heat capacity law. So that's the same. So the solution for this differential equation, when Debye did it for heat capacity in 1912, was a long time ago, he said was a sine function or cosine function. And if you plug that in, it solves that equation. And then the solution for it is that the frequency goes with the sine wave. So you can say that so the Einstein had predicted the heat capacity previous to that, and Debye came through with an answer that was better. In fact, they talked with each other. You know, they were communicating. Einstein was also in Zurich. He was a patent examiner in Bern, and then he ended up once 1909 or something. Then he moved to Zurich, and I think he was at the same school, University of Zurich, which I guess is kind of like the Harvard. It's like Harvard and MIT in a sense in Boston. You know, Zurich's a small town. It's smaller than Boston, so it's a little bit different, but basically there's some kind of relationship between University of Zurich and ETH. And ETH is by far the best school in Europe. You know, it's like, and everyone like thinks it is because they have unlimited money. Graduate students at University of Zurich get 50K a year. Undergraduate engineering students get paid like 40K a year. Yeah, you get paid to go to school there. So, but they're pretty selective, you know, so you have to fight for a seat, but basically they pay you while you're an undergrad. So, and they're pretty good students, you know, they're not as good as the German students, but basically they're pretty good. So money doesn't really buy you stuff, but anyway, so he ends up predicting this whole thing. And then this becomes like in his case, this thing is a fixed size. So wherever that thing is, so he's got a fixed size of these kind of break apart because he has atoms in the end. He can't get smaller than an atom, right? So I'm mentioning this because the only contribution Rouse really made was to say that fixed size was a polymer, was a Gaussian chain unit. So you could say that the size of that is NL squared, the square root of N times L, right? So it's a Gaussian chain. Then the friction factor follows Stokes' law, which has to do with the size of it, which you can also get from so you can get the spring from the rubber elasticity, from the energy of a Gaussian chain, you get the friction factor. So he just plugged those two things into this Debye model that already existed since 1912 and 53, so 41 years later, you know, and then he came up with the Rouse model and the solution, and he also proposes a sine wave solution to the thing. So he predicts that it's going to have like e to the I whatever. So that's basically a sine wave. And then he solves it and he gets an answer almost the same as this for the, in that case, for the tau, for the relaxation time, which is like 1 over the frequency. So Debye's getting the frequency, Rouse is getting the relaxation time, but they're related to each other, right? They're kind of the same thing. Einstein said there was one relaxation time. The Debye thing ends up being that it's this, so the Einstein's a single relaxation time. This is a number versus frequency. And then Debye says there's a spectrum that ends at the Debye frequency. And then based on this model, and he can predict this relationship between frequency and energy and wave number. Sorry. So that's the dispersion relationship, which comes out of his model, which is this sine wave thing, right? And then he says, because it's an atom, so K is 1 over size, so you get to a maximum size because you reach the atomic spacing, which would be a smallest size. So maximum frequency would be the smallest size. So the smallest size is the atom spacing. You end up with this fixed zone that you can see where the energy is dispersed in size inside materials. In other words, heat capacity is how it stores energy. It's like he's saying that there's a size dependence to that, and it's being distributed through this curve. And there's a maximum frequency that it can absorb due to these vibrations. So that's called the Brillouin zone. That whole thing, like from here to there, is a Brillouin zone for a material. And then the energy is dispersed within that Brillouin zone, and it just repeats after that because you have them anyway. That's kind of in a nutshell the whole heat capacity thing for the Debye thing, which I don't think is what, maybe it's what he won his Nobel Prize for it. I don't remember what he won it for. After he came to the US, so the US was in a war effort, and they were interested in, because Japan had taken over Indonesia, I guess, where all the rubber plantations were. So we had no rubber anymore. And basically, if you got a war, you need to have rubber because you got to have tires on the trucks and things. So that was a big problem for them. So they got together, the US got together with Canada, and Cornell was one of the centers for this. So Florey went to Cornell, Debye was at Cornell. So you had like 6 Nobel laureates working on just polymer stuff during the war. And it had kind of a realistic reason, like there actually was a need for rubber and they want to make synthetic rubber. So they did invent synthetic rubber, and they produced it mostly in Canada. You know, kind of weird. In north of Detroit, Sarnia, Canada was the center for rubber production. And that company's like changed hands so many times after, but it was Polysar at one time. But anyway, so this stuff, so there's a long history to this whole thing, and it makes you wonder, like, what did Rouse actually contribute? You know, like, in fact, so this already existed, and in fact, all right. So the other thing about, so that's 1912, and then 1946. It's like during the war. Let me see if how do I get back here? I think I put this up here, but I couldn't get the paper, but so Debye publishes almost the same thing 10 years before. So 40 years before he publishes the model, basically the model, the Rouse model. And then 10 years before, should be like right here. Let me see if can I remove this thing or something? No, I already did that. I think it's not getting an updated version, or else I didn't put it in here. Anyway, 10 years before, Debye publishes, I thought I put the link like right here. New Rouse model, slide, whatever, this thing, PDF, it's not there. Anyway, I have it on that computer, but it's basically the same thing. The only difference is he went directly to his molecular model. So he didn't say like the small unit was what's come to be called a Rouse unit. So Rouse, you can see in 53, so what these things are, well, it's not important. So Rouse says that he has a chain. So Debye said, like, oh, look, that's a Polymer chain, bingo, and then I can get the relaxation time. And then it follows that same thing, that sine function for the distribution, and then you get, and then the Debye relaxation time talks about modes of relaxation for the heat capacity. So the modes of relaxation come to Rouse modes. So he said that these were kind of his idea. I mean, original idea was that was an atom. Then he doesn't say what it is. And then Rouse says, well, that thing, and he said that it was mass times acceleration as a force. And he's going to say the friction factor times the velocity. So first derivative, dx, the time, gives the velocity, right? So in this thing's second, dx squared, d times squared. But you get the same solution from either one, basically. So anyway, Rouse said that there's some unit that's made up of chains that follows that R equals n to the 1/2 L, and that there's a friction factor that's the viscosity times that R times 6 pi. Some viscosity, right? And then from that you can get the relaxation time is going to be the friction factor over the spring constant. So it's from this thing, from the NL squared thing, you get the spring constant, which is like 3kT over NL squared. So 1 over n for the spring constant. If you take the friction factor by the spring constant, then you get the relaxation time, which is going to be modified because there's all these beads hooked together. So his spring is the spring between the beads from Debye, and his friction factor comes from rubber elasticity. It comes from the Stokes law, right? So the spring constants from rubber elasticity, the friction factors from Stokes law. The ratio of the two gives us tau then. Okay, so that. Anyway, I should get these slides put together properly, but. So heat capacity, and all right, so how does this work? So we have, let's see, this is explained in here somewhere. That isn't very good. This isn't it. So it must be this first slide. Right, that's it. So you have, for viscous motion, Stokes law, mass times acceleration is this thing. Right, so that the force balance between the drag coefficient and the acceleration. So you can just say that, right? And that's a differential equation. And then if you just write that differential equation, which I did somewhere. I didn't do it here though. Well, here. Let me just do it over here for a second. There's a slide that does this, but so you have force is the velocity times the friction factor. This is the drag coefficient, and that also equals the mass times acceleration. Right. So the velocity is dv dt, and this is d squared dt squared. You have mass, and then friction factor is 6 pi r times of viscosity. And then what I want to get is the case spring. Is the friction factor of the case spring is tau. And I want to get from this exponential minus t over tau times some factor that equals the position of the thing. X is a function of time. How you can do that? You end up with, let's see, where's the linear one? This is dx. No, this is dx dt. This is d squared x dt squared. Okay. And then if you want to know x, you have to integrate these two things. You get 6 pi r in x by t. Let's see. Oh, I want to. No. I don't want to use this acceleration. I want k spring times x. That's what I want. Sorry.
So then if I pull that around, I have dx dt, dx divided by x, right? To get the exponential equals dt. And then dt times K spring over this friction factor. Yeah, right. So this thing gives, that gives ln of x by x0, and this is K spring by a friction factor, and then t minus t0, delta t, right? So that means, and then this somehow is negative. I don't know where the negative one, but it should have been negative. So it's going to be that x equals x0 exponential of this K spring by sigma, which is tau, and then up top is this t. Right, so you get this exponential decay by saying that you have a friction factor times velocity and a spin constant times x. So you have, let me write that over again. So we have dx dt, that's the velocity times a friction factor, equals spring constant times position, right? So then you can rearrange that and say dx by x equals the spring constant by the friction factor dt, and then integrate that, and then you get ln of x minus x0, or x divided by x0 equals minus K spring over the friction factor times delta t. Right, and then if I take an exponential both sides, I have x equals x0 exponential of minus K spring over friction factor times time. And this thing, we call it tau equals a friction factor, equals a friction factor by the spring constant. Or in other words, if the friction factor is 6 pi, viscosity times r over K spring, or I can say that r is n to the 1/2, the 6 pi viscosity n to the 1/2 times the step length, which they call b in this part, divided by K spring. K spring is if it's a Gaussian chain, K spring is going to be 3 kt over NL squared, NB squared, it's B, and then you'd have to n to the minus 1/2 out of that thing. And somehow it'll work out. Anyway, so this kind of works out to give you tau as a function of this. That's how you get this relaxation thing going on. So that you end up, anyway, this exponential of K spring over that times t. So this thing, so you have an integral from minus infinity to t to get the position where you are now. So you start at minus infinity, beginning of time, then you go to now, present time. And over all that time, if your particle is subject to random fluctuations by kt, like pop, 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 up, down, then so the g of t here in this response function. So if you say g of t is just a delta function, just one pop, like you hit a bell with a hammer and it rings. So that would be a harmonic oscillator. You pop it, it goes b, and it drones out, right? So harmonic oscillator. So this thing, the thing that converts the popping you do to the position of the thing, or the response, this thing's called the response function. So for the simple viscous relaxation system, which we're talking about, then that thing's an exponential decay. So that's this part D. So that's like the normal exponential decay, but there's other kinds of responses you could have. This is like your goo response, just like it decays. Right. So the other kind of, the other kind of standard response is it's a liquid. So if it's a liquid, then it just goes to the place, like you push it and it goes, and that's it. Right. A liquid just like goes to wherever you pushed it, and it stays there. And if it's a solid, it's got a Hookean solid, you push it and it springs back. Right. So those are the two classic responses. You have like goes, springs back, that's your spring constant one. Then the drag coefficient one is push and it goes. If you combine those two, you get basically this exponential decay. Like it goes and it stays, but it kind of flows too. So it does both, right? And then if you do
if you do a log of this, like log versus time, you get a straight line. The slope will be the relaxation time, negative relaxation time. Right. So that's kind of the model that everything is framed on. You can also have like a damped harmonic oscillator. So you put in the drag coefficient, but you also put in the mass times acceleration term, and then you get this harmonic response out of it. Right, so that's got momentum to it. This has no momentum. Like it's got nothing. It just decays down. So this is D is the thing for polymers. Basically, it's like you push it. So it's got a spring constant that you can, and a friction factor that you can calculate. And so whether that was known or not before Rouse, it's kind of hard to tell. But so the main contribution to Rouse was this idea of taking a chain and breaking it into smaller pieces, a smaller piece of which you could calculate these numbers from, even hypothetically. So the Rouse unit, even though he hypothetically calculates the numbers from it, he doesn't use those numbers anywhere. Like he kind of throws that away after. This is a funny kind of theory, in a sense, but the idea of taking a chain and breaking it into small pieces, you can see that evolved. So he was 53, and then by the late 60s, that had become blobs. The French took that. So this American did this thing, and the French took that idea and turned it into blobs, and then everything is described in terms of subunits of the chain, which they call renormalization. So you take the chain, you break it into subunits. So whatever you pull on it, and the force acts only on the large scale, not in the small. There's this blob size in between that accommodates it. Looks just like the Rouse blob. Looks like the same thing, but basically it's different in the sense that the Rouse blob can be any size. Like he doesn't say what size it is, and he never says what size it is. He never actually calculates the blob size. Whereas these other ones actually have a size. And they were in response to some perturbation, and the Rouse thing isn't due to a perturbation, it's just the dynamics due to KT. Anyway, so that said, so I don't want to use these slides now. So I want to use the other slides, which are somewhere here. This thing's called Rouse, the new Rouse model. All right. So anyway, you can see like instead of saying the mass times acceleration, he's using friction factor times velocity. So this is just exactly what I just did. Friction factor times velocity and the spring constant, except it's got the Debye heat capacity things. He's broken it into like units. So he has the L position, L-1, L+1 position. So he has that differential equation. Then he says, I think it's a wave solution because this thing starts to look like, I think it looks like a guitar string. So it's got a wave solution. It's going to have different modes. A vibration is going to have this wave solution to it, right? So then if you have this differential and that wave solution, so Debye got frequency goes with spring constant by mass because he was dealing with atomic systems, and then Rouse gets friction factor divided by the spring constant for the tau relaxation time. So it's kind of like it's like tau is inverse to frequency, and then somehow it works out that way. Because he's using the drag coefficient instead of mass times acceleration for the force. And then he uses the same logic though. He says it's a wave solution and there's a phase shift. So it's going to be decomposed into sine waves of different wavelengths. This del is the phase shift for the different components. And the different components, so what are the different components? So the initial solution in both the Debye heat capacity and the Rouse is that you have the continuous curve. So this is the dispersion relationship for the heat capacity, like how energy. So instead of tau, he's plotting energy versus frequency, but he gets the same curve. So this is just copied from Debye. This curve, it's exactly the same thing that Debye published in 1912, right? And then this is 53, so it's 40 years later. So then. So the solution to this is this equation. That's what's being plotted, inverse tau. So inverse tau is frequency. So Debye plots frequency versus wave number. This is tau versus del. It's the same plot. It's the same thing. Then then and the difference is that Rouse has these solutions based on the polymer chain, like the spring constant and the Stokes law of friction factor. Then, so you still have a thing, it doesn't have a solution because you have four parameters. You have Z position, you have time, you have tau and del, right? And you've come up by saying that you have two equations and you can solve for a relationship between tau and del. That's what this plot is, right? But you don't solve for tau, you don't solve for del. You don't have an answer. Like, what's the answer for where the chain is? How is it moving, right? So in order to get an answer, you need to say something. You need to state, you need another equation, right? So the other equation is there's kind of two options that are common. One is to say the chain's a circle, right? So if it's a high enough molecular weight, it doesn't matter theoretically, I guess, conceptually, if it's a circle or if it's a straight line. And if it's a circle, and you're going by the position, like position L plus 1, L plus 2, once you get to N, then it repeats. So you know the position of N plus 1 is the same as the position of 1. And that's an equation, right? And that equation you can solve it with. So you solve it, so that's called a boundary condition, right? So the cyclic boundary condition is one solution. You end up, so that basically you say ZL is ZL plus NR, then you solve for tau and you find out that there's this relationship, and you end up with defining what del is in terms of M, which is the mode of vibration. So the mode of a vibration of a thing like this means that it's the same, this is exactly the same thing that Debye did with his heat capacity. He also got modes of vibration. So you have a guitar string, right? And it's got like this mode, and it's got like this mode. So this is like the first mode, second, and you have like the third mode, however that would be, like 3 of them. And you have like whatever, and modes. So these are called overtones in a guitar. Like if you put your finger right here, you'll get that overtone. It'll make a high-pitched noise. And if you just have the whole string, it makes like a low-pitched noise. When you strum the guitar, you get all of those, but they aren't equally distributed in the noise. The main noise you hear is the lowest order mode. Like that's the tone you hear when you tune the guitar, you tune that low order mode. But it's not like a synthesizer. You don't get a fixed tone. You get that plus all the overtones, all the lower energy ones. So if you looked at the distribution of that, you'd say like G of frequency, it's going to be like this. The high frequency would be here. So this is the heat capacity plot, the Debye plot. So the distribution of modes as a function of the frequency. Like I have the low frequency is the 1. Anyway, this is 1 over frequency. Anyway, the Debye thing is something like that. And the Einstein was like, I have 1 frequency, like it's a synthesizer. And Debye is saying, no, it's got all these overtones. But there's a maximum because he's got the atoms hooked together at this position A, atomic spacing, and he can't get smaller than that. So basically, he's got a cutoff point, this Debye frequency. Right. So it's the same thing with the Rouse, except the smallest size is the Rouse unit of this thing. So this mode's the smallest unit he can do is this Rouse unit. And then basically he's going to get the same thing, but depending on which, and again, like the highest contribution is the tone. When you strum the guitar, the tone, you say it's an E tone, like the E string's an E tone, but it's got all these other E octaves. Like on the piano, you have the E, you have a low E, that would be the primary tone. But if you hit that low E, it's got all the other E's in it. Like it repeats every like 8 notes or something. Then you go like E, 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 all the way up. Whatever, they're all the same note, but it's just a different the overtones, the same thing. Anyway, so that's it. That's what he's doing. So he has, so in the end, you go through all this math and you just say, oh, only that lowest order mode matters. So it's called the Rouse time for the chain. Only the primary note of the guitar string is what matters when you play a song. You're going to have all that other richness to it, but basically, if you think about like the maximum bang for your buck, it's going to be the note that you played, right? The harmony you make is with that note. So it doesn't matter, there's all the other overtones. So anyway, that lowest, you can calculate that. You can calculate the energy of the, you end up with this function for what the contribution of each of the modes is, and you find out that it's 1 over the mode squared. It's like the lowest order mode, so the 2 would be a quarter of the first, and then it keeps going like that. So basically 90% is the low order modes. So you just say there's 1 relaxation time for the chain because of that. That's kind of the conclusion of the Rouse thing, is that you have the 1 relaxation time, it's the lowest order mode, and then from that lowest order mode, you can calculate all the taus and things from this. You can calculate the relaxation time. So you can calculate that the tau is going to go with the molecular weight squared, for one thing. And you can calculate that the viscosity is going to go with the molecular weight to the power 1 of or the viscosity goes molecular weight to power 1, right? Which is something, both of those things you could get just by intuition. Like you could say, well, it's a train, you pull on it, you add another car, and it's going to make it go slower, right? So anyway, so that's kind of in a nutshell. But again, like this guy, like this is all spelled out better and clearer, I think, in the, he doesn't, all right, nobody that I know mentions that that this thing was basically stolen from Dubai in a nutshell. Like, and all right, if you read Rouse's paper, which I have in here somewhere, but not if you read his paper, I'm looking for the Rouse model. This might be it. No, that's probably not it. I'm looking for the paper. That's back at the beginning, right? Maybe it was that last thing. The paper is definitely here. Like if you go to Rouse, it's like 1953, and it's on my webpage that you find it someplace. Anyway, he cites maybe it's just Rouse model something. Right here. That's on my webpage, but that's not what I'm looking for. I'm looking for the paper. Anyway, he says like Dubai did this thing in 46. Yeah, no, he doesn't cite the 53. That's the thing. The whole thing is the 53. Here. No, that's some sticky mouse thing. That's not it. Anyways, I'll send you, I'll put the link up there. I have it on my computer, but he says something like, he goes through the whole thing. It's copied Dubai straight through. Copy, 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 copy. And then like he puts in a light little twist. And then at the end, he says, the last paragraph, he says something like, oh, there's some similarity to this 46 paper of Dubai. He doesn't mention heat capacity, which is the entire thing, And the 46 paper is just like Dubai saying, oh, when I drew that chain, it looks a lot like a polymer. And from that, you get the dynamics. And then he goes through and shows the dynamics from it. So he basically did the Rouse thing in 46. And then like 53, the guy comes back and does a little twist and says like, he doesn't even mention the guy. I think it's pretty weird. I don't think it's, and you see like Rouse won the highest award, the Bingham Medal for rheology. So he won that in the 60s or something. So he's pretty well known like in the field, but basically seems dicey. Anyway, that's it. Let's quit. So I'll continue on this stuff, do reptation and stuff next time. We'll do something with that, with the homework.